Hello, I'm Devinder from Physics Partners. In this short film, we're going to look at how to teach electromagnetic induction. The film is part of a series to help you with your physics teaching, especially if you are new to teaching, new to physics, or just looking for some new ideas. I'll focus on some of the common misconceptions students have and give you ideas for introducing the concepts, especially if you are teaching remotely. Please feel free to pause and take notes, or rewind and watch again. Electromagnetic induction is quite a challenging concept for GCSE students. Some exam boards refer to it as the generator effect. Have a look at a typical 6-mark exam question. A coil of wire has been connected to a centre zero scale ammeter. Students are expected to explain why the ammeter registers a current when the magnet is slowly moved towards the coil. You can pause the video and have a go at this question. We will go through the answers later in the video. Let's start with this simple demonstration. I have a coil of insulated wire with a small LED that has been soldered onto the ends. An LED will light up when a current flows through it. But do remember that with an LED, the current needs to flow in the correct direction for it to light up. At the moment, there is no chance that LED will light up because we have no power supply to provide the current. It is important to emphasize this to your students. There is no battery attached here. It's simply a coil of wire that's been connected to an LED. However, watch. My right hand now, I have a magnet. And when I slide the magnet into the coil of wire, the LED will momentarily light up. Just having the magnet near or stationary inside the coil doesn't seem to work. It seems we need the movement and the magnet to produce a current to light the LED. I should emphasize that if I had a bulb rather than an LED, it would also light up when I pull the magnet out. But remember, the LED doesn't light when the current flows in the opposite direction. It doesn't matter if we move the magnet or move the coil as long as we have relative motion. Another way to demonstrate electromagnetic induction is to use a single wire rather than a coil. This instrument to measure the induced current is called a light beam galvanometer. Basically a very sensitive ammeter. You may find one lying around in a cupboard in your prep room. Before I continue, I should add that students notoriously confuse electromagnetic induction and the motor effect. So it might be useful to have a demonstration of the motor effect set up nearby so that students can see the distinct difference between the two phenomena. Back to electromagnetic induction. Here I have a magnetic field. So slab magnets, and you'll see that when I bring a compass nearby, it is pointing away from me. That tells me that this end is a north and the opposite end of the magnet is a south, and the magnetic field lines are moving away from me. The pointer of the galvanometer you'll see is lit up, and in the center, when I move the wire down, the pointer moves in one direction. When I move the wire up, the pointer moves in the opposite direction. If I keep the wire just stationary within there, you'll see that the pointer doesn't move. So once again, this idea that we need the movement and the magnetic field to induce a potential difference. What we can say is that the wire cuts through the magnetic field lines. There is a method for determining the direction of the induced current called Fleming's right-hand rule, although do check that it is part of your exam specification. Arrange your right hand so that your thumb, first finger and second finger are at right angles to each other, as in the diagram. Point your first finger in the direction of the magnetic field, from north to south. Point your thumb in the direction of the movement of the conductor. Your second finger now points in the direction of the induced current. If you are going to teach Fleming's right-hand rule, then make sure that your students know the difference between Fleming's right-hand rule and Fleming's left-hand rule, which we use for the motor effect. We can use my setup here to apply Fleming's right-hand rule. So in my example here, the magnetic field was pointing away from me. So my first finger needs to point away from me. Now I'm going to move the wire vertically upwards, and that's when my thumb is pointing upwards. So my second finger is pointing from right to left. That means if I move the wire vertically upwards, the induced current flowing through this wire, assuming it's part of a complete circuit, will be in that direction there. If you do not have the equipment to demonstrate electromagnetic induction, or you are teaching remotely, you can use the following effect simulation. It is called Faraday's Law. You can see we have a coil of wire attached to a light bulb, and then a voltmeter connected across the light bulb to measure the potential difference. Once again, a moving magnetic field will induce a potential difference and drive a current through the bulb. Highlight to your students that a faster movement leads to a greater induced current, and so the bulb will be brighter. So we have a look. If I move the magnet, we have a change in magnetic field, and we induce a potential difference. If we move the magnet in the opposite direction, we induce a potential difference, but in the opposite direction. A faster movement will induce a greater potential difference. And also you can show here that if you reduce the number of turns on the coil, then you induce a smaller potential difference. These examples of generating electricity have a huge application in power stations. Here is an example of how continuous movement of a coil of wire in a magnetic field induces a current and lights the LED. If I turn the handle, you'll see the coil of wire moving. I'll now introduce the magnetic field. Turn the handle and you'll see the LED light up. In power stations, the generator would consist of huge insulated coils of wire and electromagnets. Here, I am providing the movement. In power stations, high-pressure steam produced by burning fuels or the nuclear fission process would drive turbines to produce this movement. Let's go back and have a look at the exam question. Firstly, students need to highlight that there is a magnetic field around the bar magnet. As the magnet moves, the magnetic field will also move. This will get them the second mark, and cuts through the coil, which gets them the third mark. Alternatively, you can say that the coil is experiencing a changing magnetic field. This induces a potential difference across the coil. Students are expected to use the correct terminology here. The final 2 marks are for realizing that we have a complete circuit, and so an induced current will flow through the wire. Induction hobs are becoming more and more common in households as a safer option to conventional hobs because the surface does not get hot. Your students should be in a position now to understand how an induction hob works. The coil under the surface of the induction hob has a large alternating current flowing through it. This produces a changing magnetic field. Any pan placed on the surface will experience this changing magnetic field. That means a current will be induced through the pan. This current will cause the pan to get hot, which will in turn heat the food. I hope that's been a help in teaching this topic. Here are the links to the simulations I showed you, and a link to some resources that you may find useful. Hope to see you again soon.